So I'll talk about this research data infrastructure behind HTM database, and I'll present this talk on behalf of myself, who is a scientist in Materials Science Center at NREL, National Renewable Energy Lab, and Caleb Phillips, who's my main computational collaborator on the data science side of things in Computational Sciences Center. And most of the work that I'll show you today was actually not externally funded. It's some small bits and pieces of internal funding and funding of other unrelated projects that led to both the database and research data infrastructure behind it. So by means of introduction, I come from National Renewable Energy Lab. It's a DOE-funded national lab in Golden, Colorado, near Denver. So this is over here, Golden. It's at the foothills of Rocky Mountains. These things here are foothills. Rocky Mountain is actually over to the left with a lot of snow on the peaks. It's very old research institution. In 1978, it's been around as Solar Energy Research Institute. In the 90s, it got expanded and gained the status of a national lab by looking not only on solar energy research, but also wind, bio, and many other energy-related technologies, including analysis for them. It's about 2,000 people research institution with 100 million, and then just by means of background of where I come from. Specifically, I represent a materials discovery team in Materials Science Center at NREL, where we focus on and aim to discover new materials for a broad range of energy applications. Historically, it has been a lot of new photovoltaic absorbers, and more recently, absorbers for photoelectrochemical water splitting. We also work on energy conversion materials such as thermoelectrics, piezoelectrics, and ferroelectrics, energy storage, including batteries and materials for fuel cells, and very importantly, recently, energy efficiency, specifically new wide bandgap semiconductors for power electronics. In addition to this applied research topic, our materials discovery team looks at fundamental and works on foundational material science that underpins these discoveries. Specifically, we develop new high-throughput experimental, or as they sometimes called, combinatorial research capabilities, as well as do fundamental materials discovery in spaces of, for example, nitride semiconductors or metastable materials. A couple of examples of new high-throughput experimental and related tools that I'll show you today pertain to data tools that underpin high-throughput experiments, and these include high-throughput experimental database that we published 4 years ago and made publicly available as well. COMBIGER, I'll mention, as a research package for processing a large volume of high-throughput experimental materials data, and most recently, research data infrastructure, actually the backbone of these various different products that we have we have paper about and patents accepted and will be available pretty soon. So here's a typical research flow that we follow with our high-throughput experimental materials research for materials discovery. We often start with theoretical calculations, for example, from first principle simulations, or perhaps science or chemistry-driven hypotheses. Perform combinatorial experiments that in our case often are made in physical vapor deposition way. We co-spot or co-deposit, co-MBE, co-PLD, different metal targets in the presence of various gases to form sulfides, oxides, nitrates, lithium-containing materials, very broad range of chemical compounds, mostly focusing on inorganic, solid-state type materials, rather than polymers or small molecules. Have broad range of characterization techniques, all for measuring composition, structure, and various physical properties of the compounds, with the common theme that all of them have spatial resultant computer-controlled XY motion stages that allow us to probe the combinatorial gradients of composition or temperature that we create across our libraries in an automated way and gain large amounts of information about the properties that these materials have. Finally, this cycle itself repeats. We have a feedback loop here, including data analysis that I'll talk about today, but also the output of the research that we do in materials discovery team in forms of publication or patents or knowledge transfer are used to do more applied optimization type of research, for example, in gaining high efficiency in creating these materials into solar cells or other functional devices. And so basically the bottom line here is that we use a lot of these high throughput combinatorial experiments to discover new materials. This is nice cartoons, but this is actually maybe less so nice, but very realistic picture. So what this instrumental infrastructure behind materials discovery at NREL look like. You can see here examples of 7 different combinatorial chambers that we have focused on various chemistries. We try to separate chemistry to ensure high purity of the materials, as well as a selection of a couple of spatial resolve characterization tool for composition, structure, and property measurements. I guess the point of this slide is that this instrumental infrastructure have taken a lot of time, decades at NREL to develop, and we have a lot of it. And if any of you are interested in gaining a lot of experimental data from any of these characterization tools for any of the materials chemistry that we could deposit, we of course are very open and welcoming for collaborations that we could have. So just contact me after if you're interested. So that was a background of where I come from and why we do the research that we do. Let me now say a few words about high-throughput experimental materials database. One of the main side benefits or side outcomes that resulted from doing this high-throughput experimental research for the last decade. To motivate the creation of HTEM, I'd like to talk about the trade-off in data sites and data diversity among various computational experimental databases that exist out there. If you look at some of the European databases, like many people represent here, as well as American computational databases, including Materials Project, AFLOW, or OQMG, one would notice that the size of these databases is very large. They can trade perhaps 100,000 materials, and they also quite diverse. They include structure of the materials, their stability, and large number of properties. This is unfortunately not the case in experimental databases. Some of the largest experimental databases like ICSD or ICDD are structural databases. They contain only information about the structure of the materials, whereas those that contain properties like Langland-Bushman database you heard in the last talk are of course very nice, but they're significantly smaller in size than ICSD and ICDD. And there are of course examples that are kind of in between. This basically creates a trade-off in data size versus data diversity of these experimental databases. Even maybe a bigger problem of this trade-off is that none of these databases contains information about synthesis conditions, about how the materials that the properties are reported of are made. And as I think Claudia pointed out in the introductory talk, a lot of oftentimes properties of the materials in experimental world depend on how exactly they have been processed. To try to fill this experimental gap, at least partially, we developed high-throughput experimental database that I'll talk about today in the first part of the talk. But also there are in more recent years, 2020 and 2021, examples of other experimentally driven databases such as MEAT from Caltech and Hybrid DCube that Volker just talked about, that basically trying to provide in a similar way to HTM large and consistent experimental data sets that include not only structure, but various properties of materials and perhaps some of their synthesis recipes. So here's the content of HTEM-DB, high-throughput experimental database for short, as it was approximately a year ago. At the time, we had more than 7,000 sample libraries, these objects that we create with composition or temperature gradient in our high-throughput experimental materials, which each of which has approximately 44 unique points on which these libraries are mapped, resulting in more than 3,000 unique samples or entries in the database. We have synthesis conditions reported for most of these libraries, and they correspond to typical synthesis conditions of techniques like magnetron sputtering or pulse data deposition or MBE, so physical vapor deposition methods for inorganic materials. Both thermodynamic properties like temperatures at which these materials are grown or pressures, as well as more kinetic materials that is often computationally difficult to capture, for example, fluxes or rates of gases or metal precursors that have been used to synthesize these compounds. For approximately half of all of this information, we have some ways in which the sample libraries have been characterized by measuring their composition, structure, electrical and optical properties as reported in the public version of the database. So we measure structure by X-ray diffraction, composition often by X-ray fluorescence, also other technique, but X-ray fluorescence data is what's reported in a database. Electrical properties by 4-point probe methods, and optical properties by UV-vis transmission reflection spectroscopy. And approximately half of all of this data are publicly available. The rest of it is either hasn't been published yet and released, or decision has not been made on publishing it, and therefore it's possible to release, or the data comes from a project that was funded by private entities that would rather keep that data, including what materials the data was made for themselves. In terms of actually what materials we have in the database, these are, as I mentioned, inorganic compounds, often oxide nitrides, sulfides or selenides or tellurides, as well as phosphides and lithium-containing materials. And these are a selection of 33 most popular metal elements that are bound with these non-metals to make the compounds. So all along here, I would say that the number of entries that we have in this high-throughput experimental database is comparable to the size of some of the computational databases. And perhaps one advantage that this database, or one complementary feature that this database provides compared to computational databases, that actually contains explicit synthesis information for all of the samples that and all the entries that are included in here. Perhaps one of the disadvantages that some of the data here is focused on a smaller number of chemical samples explored in larger number of statistically significant points. For example, when we create a compositional gradient across one specific material, all the 44 data points here would have the same set of elements created, and they only vary by changing the stoichiometry. And this point is just, I guess, a difference with respect to computational databases. It can be viewed as advantage or disadvantage depending on the vintage point. Here's the way to access high-throughput experimental database in the most simple way, through its web interface. If you go to htm.nrel.gov, the public URL that has been around since 2018 for this database, you would find something like a periodic table where you could type in the elements of the interest that you would like to search for experimental data, and then this process navigation bar on the top will guide through different steps. If you click on the next step to filter, you would find information about all the possible libraries and samples on these libraries that contain the selected elements. And you could filter these libraries as well by how or when or whom they've been made by, as well as what synthesis conditions have been used. So in this filter results, you could see some metadata about who made these samples and what properties for them have been measured and what elements they contain, as well as some information about how exactly the samples have been made. After filter, the next step is to click into visualize, and you could look both at the raw data as it comes from instruments for these data, for these samples. For example, X-ray diffraction spectra here plotted for 44 points on the sample library for this particular library, as well as optical absorption spectra. Or look at derived properties that come from these spectral or diffractograms. For example, here we plot the thickness of the sample across the sample library. You could see a little bit of thickness gradient going across X and Y dimension of that sample library. Or you could do cross-correlative plots, for example, choose to plot the average visible transmission as a function of thin content of that sample, and color the plots by, for example, number of peaks that exist in X-ray diffraction, or do the same type of plots with resistivity or conductivity or bandgap of the material that have been extracted from these data. This is a more simple way of visualizing the data, and the one that works well for people that are just interested in finding out what kind of materials we've been working on, what synthesis conditions we use to grow these materials, and what properties they might have. If you come at it more from the data science perspective, interested in using our data for machine learning, let's say, the simple view in WebUI that I mentioned provides you a somewhat limited way of seeing the data. Here, as I mentioned, we could see, for example, for synthesis conditions, only metadata associated with the sample, as well as a few basic, most important, I would say, synthesis parameters, such as substrate temperature, the pressure at which it was grown, the time at which it was deposited, and the relative fluxes of both the gaseous and non-gaseous precursors. If you are doing more in-depth machine learning studies, this information for synthesis may be insufficient to do predictive descriptive of how to synthesize samples. So in that case, you're welcome to use the API that we have developed for HTEM-DB. And in that way, you would get a JSON file like this, which contains much more information about other samples that are other conditions that are relevant, but perhaps less important for general audience. For example, base pressure that was existing in the chamber during the synthesis, and various kind of forward and reflected power on the metal supplies, the gas flows on the gaseous supplies, and many other details. In addition to providing this API with substantial documentation in how to form the queries, we also have Jupyter notebooks with a couple of examples of how to use this API. So if you go to this link at GitHub, you'll find plenty of HTM examples showing you how to do some basic queries against our API in retrieving the samples, and then digging deeper into them and looking at their synthesis conditions and properties. All right, so this is some information about more in-depth analysis of the synthesis conditions. And I also mentioned that besides synthesis conditions, which I think is one of the most important advantages of HTM-DB, we also have more standard structural, compositional, and optoelectronic properties reported. So let me now show you a few slides about what we've done in analyzing and processing these other properties. So for chemical composition, I mentioned the distribution of different elements, metal elements that we have combined with oxygen, nitrogen, and other anions in the database to form inorganic compounds, to try to understand better how these chemical elements are actually grouped together, because often they are not binaries. For example, copper oxide or zirconium oxide, they are ternaries. We've tried this, we've used this distributed stochastic embedding t-SNE algorithm. It's a very interesting dimensionality reduction model that is used in other applications to try to collapse multidimensional spaces like this 40 or 50 dimensional space of chemical space of elements into a simple reduced coordinate dimension of dimension of just 2. So here you could see that in this type of analysis, we would find that many of our materials, different combination of elements now, form these types of lines, and the other one forms clouds. Lines correspond to pseudo-binary composition spread. For example, if you deposit copper oxide and zirconium nitrate, zirconium oxide in the gradient, we would have a line like this. Whereas some of the clouds here correspond to ternary composition spread, such as this zinc, titanium, tin oxide case that I was talking about earlier. And this seems to be a very effective way for us to visualize all the different interrelation of elements that we have in our database to perform more in-depth chemical analysis in them, as well as understand how some samples in our database related to others. For example, one may expect that the synthesis conditions used for this particular line could be similar to that particular line, which or the one that would fall in between of a hypothetical material that haven't been synthesized, and that could be useful for synthesizing future materials. We have also found ways to process large amount of crystallographic information that we have in form of X-ray diffraction in our database, and something more meaningful than just X-ray diffraction pattern. So this, we have more than 100,000 X-ray diffraction patterns that is available, and this plot here shows a very compressed selection of only 1,000 of them. So that's just a fraction of what we have in the database. That corresponds to one specific material system that contains zinc, nickel, cobalt, as well as oxygen. We have tested and optimized a particular machine learning algorithm that enables us to convolute the composition measured for each of these X-ray diffraction patterns with the similarity of X-ray diffraction pattern itself to perform specular clustering. So we have this custom distance metric in the composition and structural space that we use to perform sample clustering and look at the similarity of different samples that we made, both in terms of proximity of their composition, as well as the similarity of diffraction peaks that they have. And running such analysis on this particular data set results into something like this. So this ternary plot here represents, for the same composition space, prediction for what the phases would be in this space. So there's one specific red phase here that we know is now is a spinel single phase, and then two other phases, there is a spinel plus rock salt or spinel plus wurtzite. So essentially, applying this machine learning algorithm, this spectral clustering against our composition and structural data lets us create structural phase diagrams, which is very useful because that's the type of information that can be directly compared to, for example, convex hull calculations or more advanced temperature, including convex hull calculations from theoretical databases such as NREL Materials Database or a number of any other ones. All right, so I talked so far about the analysis of composition structure. The other two examples would be optical absorption, electrical properties. We've developed algorithms to take that transmission and reflection spectra that we measure on our instruments and report in the database, convert them into absorption spectra, and then automatically extract bandgap from these materials. So this is often done by tau plots, and we have benchmarked several different ways in constructing, in processing the data to make these tau plots, as well as then extract the bandgap out of these tau plots and benchmark them against the theoretical GW calculation that exists in NREL HTEM-DB. I'm not going to say too much about this except to highlight that this algorithm replaces often very subjective manual process that is quite often biased in extracting bandgaps out of experimental measure optical absorption spectra with something that is much more unbiased, mathematically consistent and scalable to be applied across tens of thousands of optical absorption spectra that are measured and reported in HTEM-DB for extracting bandgaps out of the spectra as a quantity that can be directly compared with theoretically predicted bandgaps. Finally, we have applied or used the random forest method to predict electrical conductivity reported on large number of semiconductors in our database. And we used both chemical composition, X-ray diffraction features, as well as deposition conditions for training this data set by tenfold cross-validation, which was around 25% of sample libraries. So with the training set of only 16K data, which is what we had at that time when we were doing that study, we created a model that predicts electrical conductivity within the accuracy of maybe 1 or 2 orders of magnitude, which may seem like very bad accuracy, but thinking about the fact that for semiconductors, and I really mean semiconductors all the way from narrow bandgap, almost metallic materials to pretty much insulators, this quantity of electrical conductivity or doping level varies by maybe 10 or even more orders of magnitude. So this type of prediction based on the synthesis data that we have, as well as diffraction and data and chemical composition, seems to be still pretty good accuracy to us, at least trying to understand which materials would be more conductive or less conductive, more semiconductors or more metals, more insulators in for the types of synthesis that we do in our lab for HTEM-DB. So to summarize, we do a lot of high-throughput experimental materials research at NREL and create a database that contains this information. Currently, internally, more than 300,000 materials, composition, structures, and properties. And then that is accessible through both Web UI and API. This large data set that we have enables scientific discoveries using machine learning methods to experimental materials problems now, in addition to well-established field of applying machine learning methods to computational data. Maybe most important conclusion that we have taken from these couple of years of past research was that creation of HTEM-DB and subsequent materials data applications would not have been possible without research data infrastructure. So in the next couple of slides, I would like to spend some time describing what the research data infrastructure at NREL is, how it has been built, what features it contains, in the spirit of this workshop on FAIR-DI to explain how we actually do it on the back end, under the hood, so to speak, at NREL behind HTEM-DB. And this is the more information along these lines would be in this forthcoming patterns article. To motivate this, I would use a quote from my colleague Caleb Phillips, who helped to build a lot of this research data infrastructure. He says that data plumbing is the inglorious work that supports modern data science, would it be in material science or many other areas of modern data science. So 80% of the time is often actually spent on plumbing, on extracting the data, processing it, organizing it, and only 20% is actually spent on doing data science and material science with the data that has been extracted. So there are two main data streams that exist around the experimental workflow that we have at NREL. I talked about how we do deposition. Often we do also various kinds of post-processing, such as annealing and spatial resolved measurements. The corresponding data flow that results from use of all of these instruments can be divided into digital data collection, digital data flow, for which we have this research data infrastructure. The data flow goes into this data warehouse and gets extracted, transformed, and loaded into HTEM-DB, as I'll discuss later, as well as metadata flow. So here we use laboratory metadata collector, a special tool that we created to help us capture the metadata that was associated with depositing of the sample or doing the characterization. And both of these data flow are, I think, equally important parts for any research data infrastructure that could be designed in another laboratory. Digital data captures the actual data, for example, diffractograms that are being measured for sample, whereas the metadata captures what conditions these diagrams, diffractograms have been collected on, or what conditions the samples have been grown at. And it's impossible to do meaningful, I would argue, machine learning on experimental data without knowing both of them. So let's look a little bit deeper on these two data flows. So for research data infrastructure part that has to do with a digital flow collection, the main important components of it are data warehouse. It's an essentially time and instrument sorted archive of data, as well as associated automated data harvesting tools that serves as a first collection point of the data, where all the data from different instruments flows. The second important component is extract, transform, load, ETL process, as we call it. It's a process that extracts meaningful and relevant scientific data out of the various proprietary, non-proprietary data files that have been collected out of these different instruments, and transforms them into something more meaningful, like an ASCII file, where this data could be cross-compared or cross-correlated or convoluted to obtain the right data. And finally, a load process, where we load different types of data, for example, composition measurement, structure measurement, and some property measurement for one particular sample library, and center it around the library concept and associate it with the synthesis data. So we go kind of from the instrument-centric view of data collection to sample-centric view of data collection, where this data can be compared and cross-correlated, and science can be gleaned, specifically synthesis, structure, property relationship, which is often mantra of material science. So this is the pictorial view of there is three most important RDI components: data warehouse, ETL process, and the application programming interface that is behind the HTEM-DB that we used for building the web UI for HTEM-DB, and that is behind the API that you could access directly. And all of this has been built over the past 10 years. That basically data plumbing, the kind of thing that Caleb says we should spend 80% of our work on, and to enable the remaining 20% of machine learning for materials research. If you look kind of one level deeper about how these different research data infrastructure components have been created, on the data warehouse side of things, it's basically a Postgres SQL database and a lot of bash script and some custom C++ code that is behind the data harvester that takes the data from tools and puts it in the database. He'll have a lot of Python for the ETL code here, that as well as some R and other custom code that basically extract the data from these custom files and put them again into relational Postgres SQL database. And then the front end here, the API and API implement uses Express, Node.js, as well as a little bit of Python as well, and some Jupyter notebooks to provide examples of that API. And all of this, you could see, is very diverse, right? We have full software stack here, which is understandable. Very different parts of the research data infrastructure require different software tools and therefore different programming languages. But also it reflects the fact that a lot of this research data infrastructure has been built with very small amounts of effort. For example, here it was one guy over a course with 20% of his time over a course of 10 years. And here there was some other person that did that, and different people have different preferences of how to build it. So this is just a reality of not having dedicated external funding for in the US for these types of endeavors, and building things from ground up rather than in a design and orchestrated fashion. All right, so now to describe at the high level what these research data infrastructure components are and how they implemented from point of view of software, let me show you what they look like roughly from user perspective. So data warehouse, as I mentioned, is something that harvests and stores all the digital files that are generated during materials growth and characterization process into a central lab and tool and date-based archive. So here you can see different tools are sorted by different labs. In different labs, there are different tools. And if you click on a given tool, there will be different dates in which the tool has generated the data. And then inside of these folders will be files. So it's like a time-step permanent record of all the data that has been generated and collected. An important feature that enables the data warehouse is what we call data harvester. It's a set of different custom codes written mostly in C++ that monitors activity on instrument computers that generate the data and automatically targets, identifies the files that have been recently either created or updated in order to pull them out, identify them in a new file, and add them to this data warehouse. The instruments, the computers are connected to the data harvester versus a special firewall isolated subnetwork. It's not part of official NREL IT network that is subject often to various ND and government mandated security updates and other special requirements, which often incompatible with the sensitive instrumental equipment that we have that throughout the instrument. So we had to create a special subnetwork for these tools. But that's another reality of doing high throughput experimental data science and data analytics and data collection in very much an experimental laboratory would be university or national lab. Perhaps maybe most important feature that I'd like to mention about this data warehouse, that was also mentioned 2 talks ago, I believe. So this data warehouse actually does not putting data there, data harvester, using data harvesters does not include any software to be installed to instrument computers. So often experimental instrument owners would be very wary of installing additional software because of its potential to interfere with the measurement process or break some of the old computers that frankly are used to run experimental equipment quite often. In this particular case, all we have to do with this data harvester approach is that they live on a central server, and the server reaches out to a specific set of open folders that are open for harvesting on that particular instrument and identify and pull all the tiles. So there is absolutely no user input and there is no interaction with the data collection software that is required, and that really enables the large size of this data warehouse that we have. So for high throughput experimental database, I mentioned we have this data collected from more than 300,000 samples, but this is actually operating across very large number of labs and buildings at NREL and different types of not only materials discovery, high throughput experimental data being collected using these data harvesters. Second important component of RDI is the extract, transform, load, or ETL process. Basically has 3 parts. A lot of Python code, R code, and Ruby code that is written, and I don't know how to represent it. I can just show the GitHub repository that we have for this. But basically, find the relevant folders in the data warehouse that have names that correspond to file name conventions that we use to name our high throughput experimental samples. Targets only these files that are relevant to our materials discovery work, copies them to a special repository that only now includes high throughput experimental data, then it extracts the files from data and transform it often from this proprietary original formats to final formats. Often we had to do very painfully some reverse engineering in these proprietary formats to be able to do steps, at least for some of the instruments. And finally, aligns individual pieces of data centered around a single sample, so that we, for example, could take thickness from one measured from one instrument, and then optical absorption, transmission, and reflection spectrum measured in the other instrument, and then put them together to calculate the optical absorption spectrum and extract the bandgap from that. This repository of the code here again has been constructed over the past 3 or 5 years, and all very much ground up. Haven't really refactored this code to make it publicly available. However, I would point out that the structure of that code and its philosophy is basically built on what we call COMB-Eager, and COMB-Eager is an open source data analysis package that we use essentially to prototype this ETL process, and that is publicly available. And you could get an idea about how this ETL process works from this COMB-Eager package. So let me just intervene now and say a couple of words of this COMB-Eager. It's something that we released publicly through this web page as well as on GitHub a couple of years ago, and published a paper about this in ACS Combinatorial Science when the journal was still alive. It's a code base. It's a plugin for commercial software analysis tool called EagerPro that we tend to use a lot of NREL, that is focused on loading various kinds of data files that come from high-throughput experimental research instrument that we are using, processing and organizing around the samples, kind of like our ETL code does, and then has a lot of advanced graphics functionality for making correlation, plots, and analysis of these data with each other. It's a very powerful tool for people that are interested in high-throughput experimental research, and it's also open-based. You could develop new instruments, meaning new instrument loaders for this code, using templates that we have here, as well as new plugins, for example, different other ways of visualizing and processing the data. But that's probably as much as I'll say about this COM-B in this talk, because the audience here obviously is different. It's not high-throughput experimentalists so much. Only to say that this COM-B code and structure is basically a similar way in which the ETL process mentioned in the previous slide has been designed. Finally, I think I started the session by talking about the importance of both digital data that we collect from different instruments as well as metadata. And metadata is, I think, equally important part of the experimental data stream. It's something that describes how exactly the samples have been measured, or how exactly they've been synthesized beyond some log files that can be extracted automatically from synthesis chambers. And it's very, very difficult stream to capture because it requires interactions with humans, right? Somebody has to go and, instead of writing in their lab notebook about how experiments have been made, or in addition to writing in a lab book, also fill out some sort of digital form to digitize this data. So we've tried many different versions of lab metadata collection over the past 10 years. It's probably third or the fourth version of the design that we're finally converging on, and seems to have all the features that were not quite there in the previous version. So LMC in its current implementation is a web-based form, lab metadata collector, that is done per instrument. So every instrument would have a form like this. In its very simple form that is dynamic. You could expand this as you go. For example, if you're using additional target or gas sources for metal or gaseous precursors, and then put in information of what exactly parameters were used to synthesize this, as well as that nodes or data that cannot be captured by this form. It's very easy to complete. It really takes like 30 seconds for somebody to complete, and we find that having this very short and very informative form that users can complete actually works. The motivation that the users have to complete this form, rather than just ignoring it and writing things in an old way in a lab notebook, is that they could take the files that are generated this form, the JSON files, and actually, once this form is created, load these files into COM-B, which is the software platform that they use anyways to analyze their data. And this provides motivation for them, right? They basically digitize their data, they convert this into the JSON file, and they load it into Eager so that they could actually then correlate their measured properties in the sample structure that they create with the synthesis conditions. So having something for user to do with the data that they are spending time putting in, we find is a very important motivation factor for success of lab metadata collection tool in its present implementation, or in our prior Python-based or LabVIEW-based implementations. All right, to summarize this part of my talk, research data infrastructure is really a critical and enable component for HTEM-DB. We have two important data streams: digital data collection, laboratory metadata collection, and laboratory metadata collection I just talked about for a moment. Digital data collection has several important components. One is a data warehouse, which is the lab, instrument, and time-sorted archive of files. Have an extract and transform load process with underlying relational Postgres SQL HTEM-DB that takes the files from instrument-sorted archive, puts them in a sample-based archive, and cross-correlates the data in a relational database. And finally, we have this extra layer that didn't really talk as much about of application programming interface implemented in Express Node.js that is used for web interfaces, other custom visualization programs. For example, our web UI that we have used at htm-nrel.gov to display the data that I featured a couple of slides ago uses the same API that runs against the HTEM-DB to get all the data and visualize it. And you could build yourself any number of custom application, visualization, and machine learning tools using that API. All right, so that was two main parts of my talk about HTEM-DB and research data infrastructure behind it. Let me now summarize this as a whole thing and conclude. So in terms of interesting future research direction I'd like to pursue with this data infrastructure and HTEM-DB, there's two of them, or at least two. Two I'd like to highlight is first is integrating experimental computational databases. We have there are a number of them, computational databases. We also have one at NREL called MedDB, the one that I mentioned has GW calculated bandgaps in it. We would like to try integrating this material in with HTM or experimental database because we think it provides many complementary information about materials. For example, things like effective methods that are very, very difficult to experimentally measure exist in computational databases. And then things like synthesis conditions that are non-existent in computational databases are very abundant in experimental databases. The challenge about doing this is actually linking up materials. That's at least maybe one of the challenges. We, for example, have different ways of describing the structure of material, right? Theorists often operate on things like CIF file or postcards, and experimentalists talk about X-ray diffraction patterns as characterization of material structure. And there are steps that need to be taken on both computational and experimental side to bridge this divide and to be able to link entries in the computational and experimental databases. The other interesting direction, I think, is autonomous experimentation with specifically inorganic solid-state materials. Obviously, it's a very active research area and a lot of wonderful research done both in Europe and Canada and some in the United States about doing autonomous experimentation with organic materials. And here, what I mean is both small and large molecules that contain a lot of carbon and other important elements, as well as polymers, as was talked about this morning. I think that doing something like this in the space of inorganic or solid state materials, the oxides or nitrites or sulfides or the semiconducting type of materials that are inorganic, that are very relevant and very commercially important for many energy technologies, would be extremely interesting from point of view of its energy applications. But it's also very much more challenging, right? We can't use, for example, simple spectroscopy, vibrational spectroscopy in the way organic or polymer people do to identify what they made. We have to use tools like X-ray diffraction, which are very difficult to couple with typical physical vapor deposition methods that are used to make inorganic materials. And also even just the cost itself, right, which comes with the risk. Typical physical vapor deposition tool costs something like $1 million, and it's possible to set up with maybe $10,000 only and flask type organic synthesis in the lab. So the scale of the problem and unique challenges make it this problem of autonomous and organic material synthesis is something quite unique and something I wish we could do. However, for neither of these two topics, whether it's integration of experimental computational databases or autonomous synthesis of inorganic materials, we currently have external research funding. So this is still in dreams and very small amount of seed efforts that are happening internally to try to inch into that direction. So that's in terms of future research direction and application of my talk. This slide only shows the summary and conclusions from what I told so far. Two topics I covered were high-throughput experimental materials database, that is very large public repository of experimental materials data, more than 300,000 entries that we have internally, and roughly half of them available publicly that can be accessed through both web user interface and API, with more details described in this publication, as well as underlying research data infrastructure, the 80% inglorious task of plumbing all of this data to lead to a product like this. And we've been doing this for 10 years. So we really have a lot of tools and multiple versions of these tools that are getting better and better with time about how to harvest the data, how to extract, transform, load of it, and how to collect the meta data that is briefly described in this forthcoming patents article. So that I would like to thank you for inclusion and just make a final statement that I do think that this research data infrastructure, which seems to be in focus of this conference and the workshop and the project that you guys have, is very important for experimental materials databases, not only computational ones. So I'm very glad you're doing something like this in Europe. Thank you for your attention.
Thank you. Are there questions? Don't see any hands up, so let me start. On page 13 or so, you showed this comparison of band gaps with calculations. Yeah. And I understand this is optical absorption and you compare it with GW. So how do you correct for electron-hole interactions, so excitonic effects, because GW doesn't give you the optical gap, and also electron-phonon coupling?
Yes, very good
Both are in
point.
the order of a few tenths of an electron volt. Both reduce the gap, so there must be a lot of discrepancies otherwise.
That's right. You're absolutely right. There are uncertainties both on the computational side that you pointed out, the electron-hole interaction and excitonic effects, which I'm aware from my personal research experience, are very important. But I would say maybe even larger uncertainty comes from experimental data. It's also very, very far from perfect. We find that even not comparing different research algorithms, computational research algorithms to extract the data from optical absorption spectra, but comparing interpretation of different humans to each other can lead to even larger discrepancies. So that is reflected by very large distribution of these data. For example, here you could see that the indirect data for this particular material calculated from GW lies below experimental data distribution, and the same thing with the direct band gap. But even the error bars on this GW calculations have smaller magnitude compared to error bars on experimental data that had to do with uncertainty interpretation of optical absorption spectra, as well as spread of the synthesis conditions that lead to variation of materials properties. So yeah, it is very important computational challenge to get the band gap right, but I think there's even more important experimental challenge to control the samples and to interpret data in a faithful and mathematically consistent way that people talk less about, but very, very important.
Okay, thank you. Gianmarco?
Tom Polstra here, University of Twente. Thank you for this very impressive talk. A lot of efforts and materials. I have two questions on the more general level. If you do this high throughput materials data science, I can see various aspects that are valuable, and I would like to extract some kind of opinion of you, which is more valuable. Is it more valuable to learn of new stoichiometries, new materials, new compositions that are stable and that give you the handle on new properties? Or is it that you learn more about the dependencies using machine learning, that you know exactly what kind of composition, what kind of synthesis conditions you need in order to find dependencies that are not easily observable? And I do have a follow-up question.
Yeah, I think that the first type of question that you posed can be reasonably well addressed with the modern accurate computational data science. The questions of how elements that go into a crystal structure affect the resulting properties across very broad range of materials that are accessible computationally these days could give pretty good insight into crystal chemistry trends. And I think there's a lot of very valuable publication literature these days on that topic. I do think that the experimental database and specifically inclusion of the synthesis conditions in these databases is something that would be very difficult to capture computational and provides an additional value there. You mentioned already how the synthesis condition affect different properties. The other maybe hidden variable here is how the off-stoichiometry captures the properties, right? We often make these compositionally graded sample libraries where stoichiometric material, let's say, is in the middle and there's an off-stoichiometry on the left and the right. How exactly off-stoichiometry influences the properties, in particular electrical properties, right? How it leads to self-doping of the materials is something that is extremely difficult to capture computationally. And I think these types of more subtle synthesis property relationship and various non-idealities, including kinetic synthesis conditions, as well as effects of off-stoichiometry and materials properties, is a big added value.
I must disagree with you on the first picture, but I think it's still exceedingly difficult to predict crystal structures, especially if you look at the last talk of these organic-inorganic hybrids. But I can see the advantages. But let me follow up on the other aspect, that is the composition dependence. Because if you have materials that do not crystallize in the same crystal structure, or even if they do, the properties are often very much determined by grain boundaries or by interfaces. And the exact nature of these interfaces, of course, is something that also is visible for you experimentally. So is this something that you focus on as well, or should that receive more attention?
Yeah, it's a very good question. Effects of microstructure interfaces and grain boundaries are certainly very important, more so for some applications than the others. For example, if you talk about the optical absorption spectra and the band gap, this is very much locally dominated property that is maybe less sensitive to it, but other properties like charge transports are extremely important. Sometimes very difficult to implement the high throughput experimental measurement techniques that would, in a high throughput way, provide information about the microstructure or interfaces. Often doing this from SEM or from TEM requires very involved measurements that are performed in a very small fraction of a sample compared to an, say, 2-inch by 2-inch library that we generate this in. And there could be variability of the microstructure across in the vicinity even with that sample, not even speaking across large size of 2 inches. So yeah, we try to do it maybe in a similar way that Claudia was talking in her introductory talk by staggering different characterization techniques. We measure what we can measure first quickly, including materials composition, structure, and some basic properties. And then for the most interesting cases where we do have information that particular sample is worth investigating, we look at the effects of microstructure interface, another thing that simply cannot be characterized in a high throughput way, or very difficult to characterize in a high throughput way, in this type of final fashion of the approach where you measure easy things first and then you measure harder things later.
Thanks.
Thanks. So I have one more question. When we already addressed grain boundaries, and I like it very much that you take into account the growth conditions and like the deposition. In most of these cases, you also have traces of like carrier gases still there, right? Hydrogen is one thing that is almost always still there in some quantities, and this actually influences properties of these materials, especially optical and electrical properties, even if it is like sub percentage levels in mass even. Do you have any idea of how large these quantities are in your deposition methods?
Right. Yeah, thank you for that question. Certainly there are various non-idealities in the experimental synthesis setup that may prevent from achieving ideal property of the material. We don't have direct measurements of hydrogen, as you may be aware of. These are extremely difficult. We have tools like Rutherford backscattering, for example, at NREL that conceivably can measure hydrogen in the sample, but these are very, again, specialized experiments of the kind of grain boundaries that I was talking about that just impossible to do in a high throughput way. But there are types of data in our database and accessible through API that may let you get an idea about how at least relative amount of contaminants or hydrogen are changing between different samples. So for example, not in this web UI, but if you dig deeper into the API, there is a field here under the gases that is called base_torr. And this is the base pressure in torr of our chamber. And for this particular sample, it happens to be 8 × 10⁻⁷ torr. That base pressure is pretty much entirely made out of water. And I think water or cracking of water in plasma to produce some oxygen or hydrogen that can both intentionally or unintentionally be incorporated into the sample is the main source of hydrogen. So there's probably some correlation about the amount of unintentional hydrogen that exists in our sample with this quantity called base torr. And even though we don't exactly know how much of hydrogen is there, the relative base pressure that was done for different samples in this chamber or between different chambers could be used as a relative metric of how much of this impurity could be in our samples.
Yeah, thank you. Very, very useful.